Hello everyone, welcome back to Discrete Mathematics with me Adila Krishnadi, and we are still discussing matching. Now we are at the point where we look at sufficient and necessary condition for a complete matching to exist. So in a bipartite graph, I should say, right? So only in a bipartite graph. This is called Hall's marriage theorem. Yeah. You look at this in Rosen page 693 and 694. So the statement or the theorem says is stated as follows. So if you have a bipartite graph G, yeah, this is bipartite, all right. Now this with bipartition phi1 and phi2. Now this bipartite graph G will contain a complete matching from phi1 to phi2 if and only if for every subset of phi1 the size of its neighbor is larger, greater than or equal to the size of that subset. Yeah. So that means, or to be let me repeat, if every subset of phi1 has neighbor whose size is at least the same or even more. Yeah. So the condition is that, let me just state this, for every subset A phi1, yeah, the size of A is less than or equal to the size of the neighbor of A. Now note, of course, here the neighbor here is proper, right? Because G is bipartite. Yeah, G is bipartite, right? Now the this is a proper neighbor. So the only if part is easy, obvious, right? Because obvious, because if there is a subset A in phi1 with an A less than the size of A, yeah, then some nodes in A cannot be matched. Yeah, because that, as we saw in the previous example, that when he in the previous example we saw the set Sony and Winnie, the neighbor of this is really just set of AD. So here, so Sony cannot be, if Sony is matched to AD, then Venu cannot be matched to anything, right? So that's the idea. The if part, yeah, so this is the necessary condition part. The sufficient condition, meaning that if every subset of phi1 satisfies that its size is less than or equal to the size of its neighbor, then the graph, the bipartite graph, will contain a complete matching. That is slightly more involved. This is done by induction, strong induction on the size of phi1. So start with size of phi1 to be equal to 1, and then going upward, right? You see the details in page 693 to 694 in Rosen's book, so I won't go into detail here. All right, so that's the theorem. Now let's do some exercise here. Let's apply the theorem, the Hall's marriage theorem. So given this bipartite graph, does this graph have a complete matching from from v1 to v2, where v1 is, this is v1, this is v2, yeah. V1 consists of A, B, C, D, and V2 consists of P, Q, R, S, T. So does the graph have a complete matching from V1 to V2? If not, when does the Hall's marriage condition fail? So try this exercise first, and we discuss the solution next.